Now let's do this practice together. The task 1 and the task 2 are supposed to be finished during you viewing the reading material. Let's quickly go through it. Don't forget to import required packages or libraries like pandas. Then go to Canvas to download the LC loan dataset we need in this section. In this example, we first load a loan dataset into a data frame. Then we check the basic structure of the dataset, such as the number of rows and columns. This helps us understand the size of the population we are working with. Do you remember the function calExplore that we created from the last section to calculate the probability of each category for categorical variable? We can use this function to explore the frequency of grade. Then we can do these. First, we convert all the column names in the LC underscore loans data frame into a list using the columns attribute and the toList function. And this gives us a list of all the column names, which we store in the variable called column underscore list. Next, we perform stratified sampling using a more compact and optimized approach. We start by using the groupie function on the LC underscore loans data frame, grouping the data by the grade column. The group underscore keys equals false argument ensures that the resulting data frame does not add an extra hierarchical index from the grouping. Then we select all the columns from column underscore list and apply a lambda function. A lambda function in Python is a small anonymous function defined using the lambda keyword. Finally, the apply function runs the lambda function on each subgroup, and the results are combined back into a single data frame called stratified underscore sample. Then we use categorical exploration function to explore the frequency bar chart of this stratified sample dataset. And we can find out that the frequency of our sample dataset is exactly the same as the frequency of original dataset. So this proves the correction of our task 1. Let's see how we implement the bootstrap approach in Python and how to interpret the results. First, Python does not have a built-in bootstrap function in the major packages, so we use the resampling function from the scikit-learn library. This function allows us to randomly sample from an existing data set with replacement, which is exactly what Bootstrap requires. We start by importing the resample function from sklearn.utils. Then we load the loans income data from the CSV file into a data frame called loans income, which you can download from Canvas. Calling head lets us quickly confirm that the data has been loaded correctly. Next, we begin the bootstrap process, and we first create an empty list called results. This list will store the mean from each bootstrap sample. Then we use a for loop that runs 1,000 times. Each loop represents one bootstrap sample. Inside the loop, we call the resample function on the loans income data frame. This creates a new dataset of the same size as the original, sampled with replacement. That means some rows may appear more than once, and some rows may not appear at all. After creating the bootstrap sample, we calculate its mean using the mean method. This mean value is then added to the results list. By the end of the loop, the results list contains 1,000 sample means. Once the loop finishes, we convert the results list into a pandas data frame called results table. Each row in this table represented the mean from one bootstrap sample. This table is our empirical sampling distribution of the mean. Next, we visualize this sampling distribution. We first plot a histogram of the results table with 100 bins. Setting density to true normalizes the histogram, so the total area equals 1, which makes it easier to compare with a probability distribution. Then we overlay a density curve on top of the histogram. This smooth curve helps us see the overall shape of the distribution more clearly. Both plots are drawn on the same figure, so we can compare them directly. After that, we calculate two important values from the bootstrap distribution. We compute the mean of the bootstrap means, which estimates the population mean. We also compute the standard deviation of the bootstrap means, which is the standard error. In this step, we use alog because of what the mean function returns in pandas. When we call result underscore table.mean, pandas does not give us a single number. Instead, it returns a series that contains the mean for each column in the table. Even if the table has only one numeric column, the output is still a series, not a single value. Because of that, we need a way to extract the actual number from this series. That is where alog comes in. The alog method selects values based on their position. When we write alog 0, we are simply saying, give me the first value in the series. So alog 0 means the first element, not a column name and not a label, just the first value by position. This turns the result from a series into a single numeric value. If we do not use alog, the variable mean would store a series instead of a number. That can cause problems later when we try to use this value in calculations, formulas, or when displaying results. By using alog 0, we make sure that mean is a single number, which is exactly what we need. We then create a text label that displays the mean and the standard error, rounded to 2 decimal places. The letter F before the quotation marks means this is an F string in Python. An F string allows us to directly insert variable values into a text string. Instead of combining text and numbers manually, Python fills in the values for us. Inside the curly brackets, we see min:2f, and this is called a format specifier. The .2f tells Python to keep only 2 digits after the decimal point and to display the number as a floating point value. For example, if the mean were 68,759.9876, it would be shown as 68,759.98. And this makes the output cleaner and easier to read. The same formatting rule is applied to std, which represents the standard error. Again, .2f ensures that only 2 decimal places are displayed. The \n inside the string represents a new line. It tells Python to move to the next line when displaying the text. So instead of showing everything on one long line, the output will display mean on the first line and std error on the second line. As a result, label underscore text becomes a neatly formatted 2-line message that shows the mean and the standard error, both rounded to 2 decimal places. And this kind of formatting is especially useful when adding labels to plots or presenting statistical results clearly and professionally. This label is placed in the top right corner of the plot so it does not block the data. First, we use the function put.text. This function allows us to write custom text at a specific location on a plot. The first two numbers, 0.95 and 0.95, define the position of the text. These numbers are not data values from the chart. Instead, they represent a relative position within the plot area. 0 means the far left or bottom, and 1 means the far right or top. So 0.95 places the text very close to the top right corner. Next, label underscore text is the actual content we want to display. This is the string we created earlier that contains the mean and the standard error. Then we see transform equals plt.gca.transacts. This part is very important. It tells Python how to interpret the coordinates we just gave. By using transaxes, we are saying that the coordinates are based on the plot's axis system, not the data values. In other words, 0 to 1 always maps to the plot area, regardless of the scale of the data. And this is why the label stays in the top right corner even if the data changes. The parameter HA equals right controls horizontal alignment. It means the text is aligned to the right edge of the text box, so the text grows leftward from the point we specified instead of pushing outside the plot. Similarly, VA equals top controls vertical alignment. It aligns the text to the top of the text box, so the text drops downward from that point. Putting everything together, this line places the label text neatly in the top right corner of the plot, aligned in a clean way, and positioned using relative coordinates so it does not overlap with the data or move unpredictably when the plot changes. Finally, we add axis labels and a title to clearly explain what the chart shows. We also remove grid lines to keep the visualization clean. This is how we do task 2. Now we move to task 3, which involves several real-world examples using z-scores and normal distributions. Let's start with the salary example. We are told that the average annual salary is $50,000 and the standard deviation is $5,000. And this means most salaries are centered around $50,000 and they typically vary by about $5,000. We first store these parameters in Python. Then we take 60,000, subtract the mean, divide by the standard deviation, and print the result. This tells us how many standard deviations above average this employee earns. The second question asks for the z-score of an employee earning $45,000. This salary is below the mean, so we expect a negative z-score. We'll repeat the same formula with 45,000. Next, we move on to SAT scores. We firstly store these parameters. The first question asks, what percentage of students scored above 1400? Statistically, we can calculate the z-score and then use the cumulative distribution function from the SciPy stats library. And this function gives us the probability of scoring below 1400, so we subtract it from 1 and multiply by 100 to express the result as a percentage. The next question asks, what percentage of students scored between 1000 and 1400? Conceptually, we calculate the z-score for 1000 and the z-score for 1400. We then find the probability below each value and subtract the smaller probability from the larger one. In Python, we compute both z-scores. Use the cumulative distribution function for each. Subtract them and multiply by 100. And this gives us the percentage of students whose scores fall in that range. Now let's look at a height example. The mean height of adult males is 70 inches, with a standard deviation of 3 inches. The first question asks, what is the height of a man with a z-score of 2? A z-score of 2 means the person is 2 standard deviations above the mean. To convert back to height, we multiply the z-score by the standard deviation and add the mean. The second question asks for the height of a man with a z-score of negative 1.5. A negative z-score means the height is below the mean. We again multiply the z-score by the standard deviation and add the mean. Next, we look at a test score distribution with a mean of 500 and a standard deviation of 50. The first question asks, what percentage of students score between 450 and 550? It is very similar to question 2. The main idea is still to calculate both z-scores. Use the cumulative distribution function, subtract the probabilities, and multiply by 100 to get a percentage. The next question asks, what percentage of students score above 600? We calculate the z-score and subtract the cumulative probability from 1. Then we are asked, if 500 students took the test, how many scored below 450? Statistically, we first find the probability of scoring below 450, then multiply that probability by the total number of students dot. The result tells us the expected number of students below that score. Next, we compare performance across 2 different exams. In exam A, the mean is 80 and the standard deviation is 10 and the student scored 90. In exam B, the mean is 70 and the standard deviation is 5 and the student scored 80. To determine which exam the student performed better on relative to peers, we compare z-scores. A higher z-score means better relative performance. In Python, we calculate the z-score for each exam using the same formula. Then we compare the two z-scores using a simple if statement to determine which one is larger. Finally, we look at an admission problem. A university admits students in the top 10% of SAT scores. The mean is 1200 and the standard deviation is 200, which are stored in question 1. The first question asks, what z-score corresponds to the top 10%? The top 10% means the 90th percentile. So we use the percent point function from SciPy stats, which directly gives us the z-score for the 90th percentile. The second question asks, what is the minimum SAT score required for admission? We convert the z-score back to an SAT score by multiplying it by the standard deviation and adding the mean. These are the results of practice. Please let me know if you have any confusion or more questions.